for this video, we'll be discussing resistance and resistivity. So what are these two quantities? Resistance and resistivity. So resistance is a measure of how difficult it is to pass current through a wire or a component. Basically, it's the thing that inhibits, or it's something that inhibits the flow of electrons. Resistance depends on the resistivity, and resistivity is the characteristic of the material used to fabricate a wire or other electrical components, whereas the resistance is the characteristic of the wire or the component. So electrical resistance of the wire would be expected to be greater for a longer wire, less for a larger cross-sectional area, and will be expected to depend upon what type of material the wire is made up of. Now, those things are factors that can affect the resistance of a wire. So these are the following factors. Number one, we have cross-sectional area, length, material of the wire, and temperature. For cross-sectional area, resistance varies inversely compared to the cross-sectional area. Thus, if we increase the area of a wire, then the resistance will decrease. So if you have a thick wire, then you will most likely have lesser resistance than if you compare that to a thin wire. Then we have the length. What about the length? The resistance of the wire is directly proportional to the length, and the longer a wire has, a greater resistance. The longer the wire, the greater will be its resistance since it's directly proportional, provided that it's the same material and cross-sectional area. So if you just change the length of the wire, then if you increase the length, you also increase the resistance. For the material of the wire, the effect of the kind of material on the resistance of the wire is determined by its resistivity. So resistivity is the reciprocal of conductivity, and conductors have small resistivities while insulators have large resistivities. And resistivity can be affected by temperature. So let's look here into a table. So we have here a table of the resistivity of some materials. As you can see, conductors have lower resistivity compared to insulators, because insulators are materials that do not allow the flow of electrons, or they do not have the capacity to conduct. That's why they have, or because of high resistivity, they are not able to conduct current, or they are not able to allow current to pass through. The effect of the length, cross-sectional area, and material on the resistance may be expressed in a mathematical equation written as resistance, or R, is equal to rho multiplied by L divided by A, where, of course, R is resistance, rho is resistivity of the material, L is the length, and A is the cross-sectional area of the wire. Now, this is a table showing the temperature coefficients of resistance of some materials at 20 degrees Celsius. So these are the temperature coefficients of the resistance of materials if those materials are at 20 degrees Celsius. So temperature dependence of resistance and resistivity is nearly linear if the change in temperature is not too great. So an expression like linear thermal expression approximates the effect of the temperature on resistance and resistivity. Again, temperature is a factor that affects both resistance and resistivity. So this linear relationship is given by, we have here the formula for the change in resistivity, or the resistivity at temperature T, which is equal to your resistivity at the reference temperature multiplied by the product of the resistivity at reference temperature multiplied by the temperature coefficient multiplied by the change in temperature. Then you have the formula for the resistance at temperature T is equal to the resistance at the reference temperature plus the product of the resistance at the reference temperature multiplied by the temperature coefficient multiplied by the change in temperature. So let's have here a sample problem. An insulated extension cord is made of 1.5 long copper rod with a diameter of 2.3 millimeters. What is the resistance of the extension cord? And B, if an aluminum wire of the same length will be used instead of copper, what should be the diameter of the aluminum wire to have the same resistance? So let's look into our given values. What are the given values in the problem? So we have the length of the copper wire, which is given at 1.5 meters. Then you have the diameter of the copper, which is 2.3 millimeters, which, if expressed in meters, that's 2.3 times 10 raised to negative 3 meters. Then we need to identify the resistivity of the copper and aluminum, since these are the materials that is used to make the wire in our problem. So we have the resistivity of copper, which is at 1.72 times 10 raised to negative 8 ohm meter. So you can take this value in the table that was shown to you earlier. And then for the resistivity of aluminum, that is 2.75 times 10 raised to negative 8 ohm meter. So for letter A, we are asked to solve for the resistance of the extension cord. So what is the resistance equal to? So first, we need to identify how we can solve for the resistance. Remember that our resistance can be solved with the formula resistance is equal to the resistivity multiplied by the length divided by the cross-sectional area. So since this will be the resistance of the copper rod, so we need to use the resistivity of the copper times the length of the copper divided by the cross-sectional area of the copper. We know the resistivity of the copper and the length of the copper wire. However, we do not have the value for the area of the copper wire. But for the area of the copper wire, we can solve the area of the copper wire by using our formula pi r squared or pi d squared over 4. Because our wire has a cross-sectional surface of a circle. Therefore, to solve for the area, then that will be equal to pi d squared over 4. If we solve for the area of the copper using that formula, so that's pi multiplied by the diameter, which is 2.3 times 10 raised to negative 3 meters squared over 4. So the cross-sectional area of the copper wire will be 4.15 times 10 raised to negative 6 meters squared. So now we have all of the required quantities for us to be able to solve for the resistance of the copper wire. So for the resistance of the copper wire, that will be equal to your resistivity of the copper wire, of a copper, which is 1.72 times 10 raised to negative 8 ohm meter, multiplied by the length, which is 1.5 meters, divided by the cross-sectional area, which is 4.15 times 10 raised to negative 6 meters squared. So what will be the resistance? So the resistance of the copper wire will be 6.217 times 10 raised to negative 3 ohms. So this is the resistance of the copper wire. For question B, you are asked of the diameter that the aluminum wire should be if the wire is if the material used for the wire, originally the 1.5 meter long copper rod, is changed to an aluminum, so what will be the diameter if we retain the same length and we retain the same if we want to have the same resistance? So to solve for the diameter of the aluminum wire, so we still have the length of the aluminum wire, which is 1.5, because as stated, it's only the diameter that is to be changed because you will have the same length. And of course, you will also have the same resistance. Therefore, the resistance of copper will also be the resistance of aluminum, which is 6.217 times 10 raised to negative 3 ohms. And to solve for your diameter for aluminum, remember with our formula, R is equal to rho L over A. So your diameter is in here. So let's derive an equation for the area of the aluminum. So the area of the aluminum is equal to your resistivity of the aluminum multiplied the length of the aluminum over the resistance of aluminum. So what do we do here? We substitute our values. Let me erase that one here. So we substitute our values. We have the resistivity of aluminum at 2.75 times 10 raised to negative 8 ohm meter, multiplied by the length, which is 1.5 meters, multiplied by the resistance of the aluminum wire, which will be retained, similar or same with the resistance of the copper, 6.217 times 10 raised to negative 3 ohms. Why do we have the same resistance? Because again, in the problem, it said there that what is asked from us is to solve the diameter that the aluminum wire should be for it to be able to have the same resistance as the copper rod with the same length. So now we know that the cross-sectional area for the aluminum wire should be about 6.635 times 10 raised to negative 6 meters squared. But we are not asked of the cross-sectional area. Instead, we are asked of the diameter that the aluminum wire should be. And remember, to solve for the area, area is equal to pi d squared over 4. So in deriving an equation for that, if that's the case, then therefore, your diameter of the aluminum will be equal to 4 times area of aluminum over pi, and you take the square root of that quantity. So if you substitute your value, that's the square values, that's the square root of 4 times the area of the aluminum, which is 6.635 times 10 raised to negative 6 meters squared over pi, which is, of course, pi. You can just input in your calculators pi. The diameter for the aluminum wire should be 2.907 times 10 raised to negative 3 meters. So these are the answers to this problem. Next, another sample problem. The resistance of a platinum wire at 30 degrees Celsius is 15 ohms. So you are to solve for the resistance at 45 degrees Celsius. So here is the resistivity of the platinum wire, alpha at 0.0039 per degree Celsius at 20 degrees. So what are our given values? So we are given the temperature, which is at 30 degrees. Then we have the resistance at 30 degrees, which is 15 ohms. And then we have the temperature coefficient alpha, which is at 0.0039 per degree Celsius at 20 degrees Celsius. So take note that our alpha is given at 20 degrees. However, our reference, or the given value of the resistance is at 30 degrees, and we are to solve for the resistance at 45 degrees. So since alpha again is given at 20 degrees, the reference temperature is 20. So we need to solve for the resistance 20, or R20 at 20 degrees. So using our equation, we have, first we need to solve for the resistance at 20 degrees because that is our reference temperature. Our temperature coefficient is at 20 degrees. So remember your formula. R is equal to R0 plus R0 alpha change in temperature. So you just need to change that. Your R here will be R30 equals R20 plus R20 alpha times temperature, and then temperature at 20. Or temperature at 30 minus temperature at 20. So substituting our values, we have here, we know the resistance at 30 degrees, that's 15 ohms, equals, we don't know R20 because that's what we're trying to solve here, multiplied by the coefficient of the temperature per degree Celsius times 30 degrees Celsius minus 20 degrees Celsius. So what is this? What will be the equation now? That will be 15 ohms equals, so what will happen here? So 30 minus 20 degrees Celsius minus 20 degrees Celsius is 10 degrees Celsius. Then you multiply it with the coefficient, the temperature coefficient. Then you multiply it here. Then you have 1 plus this quantity. So that is, if we look at it, that will be 1, or that will be R20 plus 10 degrees Celsius multiplied by 0.039, that will be 0.039, since it will be multiplied at R20, so that's 0.039 R20. And we have here 1, right? Therefore, this is 15 ohms is equal to 1.039 R20. So the resistance at 20 degrees is 14.437 ohms. So now we have the resistance at 20 degrees, which is the reference temperature, the resistance at the reference temperature. So now we can solve for the resistance at 45 degrees using the reference temperature R20 plus R20 multiplied by the temperature coefficient multiplied by the change in temperature, which is T45 minus T20. So that is R45 is equal to, you have 14.437 ohms plus 14.437 ohms multiplied by your coefficient, which is 0.039 degrees per degree Celsius multiplied by the temperature difference. The temperature difference is Temperature difference is 45 degrees minus 20 degrees Celsius. So that is 15 degrees Celsius. So your R45 is similar to what we did here. So your R45, or the resistance at 45 degrees Celsius, is 15.84 ohms. So this is our answer for the problem. The resistance at 45 degrees Celsius is 15.84 ohms. So that's it for our lesson on resistance and resistivity. Thank you very much for listening and study well. See you on your next lesson.